Hi, welcome everyone. Welcome to this course, an introduction to statistical mechanics in soft and active matter systems. So far, what we have studied in different things, in different ways. So, we first talked about, you know, white noise and random forces, and then we talked about the Brownian motion in details and Brownian motion, free Brownian motions, Brownian motion in under external potential, and the generalized Langevin equations, and its generalized form, the fluctuation distribution relation, the time correlation, autocorrelation functions, and time correlation functions, all these things, and also random walks, random flights in absorbing and although those are in discrete systems, random flights in absorbing walls and in the presence of reflecting walls, and so on and so forth. Now we were discussing about the continuous states, where we were talking about the diffusion equations, and we solved the diffusion equations in d dimensions. So now today we will continue our discussions in the next like what is like in the following manner. Okay, so in the following discussions we will mainly discuss about the continuous random walk and how that will sort of discuss that will sort of pave the way for the Fokker-Planck equations and all these things. So that will come into those things gradually. Okay, so let me share my screen. It's visible. Okay, so we were sort of studying this, and we stopped here. There we calculated the different moments. Okay, so we calculated different moments, and now let's continue our discussions in the next thing. So now what we will do, we will study the random walk, continuous random walk. So first we will talk about the biased random walk, because that will sort of give us the unbiased one. So now do so continuum limit of a biased random walk. So we mainly discussed about the random walks in great details, but here will sort of will speed up this process. Okay, let's say the walker starts at the site j is equal to 0 at time t is equal to 0 and the probability of going, so far everything will be in 1D, huh? For the simplistic reason, going to the right is alpha, so probability of going to the left, then beta is equal to 1 minus alpha. Let us consider again A is lattice constant, lattice constant, or we can also think about as like step, like random steps, like step length constant, and tau is the size of the time step. Okay. Now if you, the probability that worker is at the site j, the the probability that the worker is at the site j or point j or point ja at time step n, or if time step is n, then when time is in tau, is p of ja in tau is equal to alpha. That means the probability, if it is at the left of that j, and then it should go to the right with probability alpha. That means I will explain this, ja minus a at n tau minus tau plus beta p ja plus a in tau minus tau. So alpha is the forward going probability, means going to the right, and beta is the going to the left. So if it is at j at time in tau, that means at previous time in tau minus tau, either it was at j minus 1 or either it was j plus 1, and if it was j plus 1, to reach j it should go to the left. That's why the probability, associated probability, is there, right? Now here we have considered like this. So this is, let's say, equation, this is 16, this is 17. Okay. Now we sort of can write as, so beta was, let's write it as alpha minus beta. That is like, you can write it as like this. So now if you take this, then there this will be beta of alpha minus beta. So basically and pj of n tau minus tau, and basically you can write 1 as alpha plus beta. Let's say minus 1 as minus of alpha plus beta, because alpha plus beta is 1 is equal to 1, and that is as minus 2 alpha plus alpha minus beta. So you can write in this way, So now in that way you can write just a minute. P P J A n tau, right, minus P J A n tau minus tau. This is one thing. Now you can easily write as, so there is alpha p this and beta p this. So you can write as minus 2 alpha of this with p. So it becomes, let me write it first. Alpha p J A minus A n tau minus tau minus 2 alpha plus alpha minus beta p of J A n tau minus tau plus beta p J A minus plus A n tau minus tau, right. So now you just write those things in a singular way, and beta as alpha minus beta. So then beta will be, this term will be alpha was, just a minute, plus alpha minus beta. So now you write this all alpha in a same term. So this you can write as alpha as p of J A minus A n tau minus tau minus 2 p of J A n tau minus tau and plus p J A plus A n tau minus tau. Okay. Now for minus alpha minus beta, you can write it like this. This was minus, so minus alpha minus beta as minus p. So this will be, there is minus, so this will be p J A plus A n tau minus tau, and here this will be minus p J A n tau minus tau. Okay. Now if you divide both sides by tau, so if you divide both sides by tau, and multiply first term on the right hand side with a square and second term by a, such that, so let's do this thing. So if you divided this becomes, this is pjnt minus pjnt minus t by tau. Now if you do this by a square and this a multiply first term in RHS by a square and divide the second term, or this term, second term by a. Okay, and now we are using the continuum section where a tends to 0 and tau tends to 0. Let's say we are making the step length and time step very small, and also alpha minus beta tends to 0. What is alpha minus beta tends to 0 means? Alpha tends to half, beta tends to half. If you do this, then it becomes such that such that such that then first term will be alpha, this will be alpha a square by tau. Then let's say using limit, this becomes d, and limit a alpha minus beta by tau becomes c. Now if you use these two conditions, so and d and c, and d and c are finite non-zero constants. So if alpha tends to half, then d becomes a square by 2 tau, right? So now it becomes, d becomes step length by time, right? Now so d physical significance is length squared by time, and c has, this becomes length by time. Physical significance. Physical significance. Now if you now since these are like continuum model, so we can now consider j tends to infinity and n tends to infinity, such that the continuous variable, the continuous variable x and t leads to the following equation. Okay, now see here, if you make it by t, so this is a first differential equation, right? So then this will be, so first term this, let me write first term p ja n t minus tau minus p ja n tau minus tau by tau. This is then becomes dp xt by dt, right? Similarly, second term, this one minus c term, then it becomes, this becomes, so using this, then becomes minus c minus c p of minus c p of ja plus a n t minus tau minus pj, like this. So p ja plus a n t minus tau minus p ja n t minus tau, sorry, this is divided by a, so this is a. Okay, because we have multiplied with a, that's why we have to divide by a. So this becomes then minus c, this is like x, because we denoted here that, thus that the continuous of x and t leads to the following equation. Okay, so basically then this becomes del p xt delta x. Similarly, this one alpha a square by tau, this is d, so this is d, and this is p of ja minus a, let's say ja plus a. So this is like finite difference method. So this is like representation of, this is representation of differential form or derivative in finite difference term. Okay, so now it comes to be nt minus t minus 2p ja n tau plus p ja minus a n tau minus t divided by squared. Okay, so then it becomes d delta p delta x2. So now using this thing in this equation you can easily write. So now you can write, I can write this equation as del p xt divided by del t is equal to minus c del p xt del x plus d del 2p x2 del x2 del x2. So here actually such that here we missed it. ja ja and n tau train to continuous variable x and t. So so okay, so this equation, this famous equation is called Smoluchowski equation. So this equation 20 is called Smoluchowski equation. Chowski equation. Actually, it describes the diffusion of a particle under the influence of a constant field of force. So now let's discuss this term. So the first term in the right hand side is called drift term. So this is called drift term, and this fellow is called diffusion term. Okay, and this c is called mean drift speed. Okay, Now if you write this equation 20 in a form of continuous equation, so now let's say if you try to write equation 20 in continuity equation form, then this will be like del rho del p del t plus del j del x is equal to 0, where j becomes jxt is equal to cp xt minus d dp xt dx. Now this ratio of this d by c, ratio d by c is a natural length scale in the problem. So it's a measure of the relative, and it's a measure of it is a measure of of the relative importance of the drift and diffusion contributions to the motion of the colloidal particles, of colloidal particles. Okay. Now there is different number. Let's say if you talk about Reynolds number, then that is quantity LC by D. So Reynolds number, let's say if we multiply it as D by C with L, where L is a characteristic length scale let's say like its size or system size or system particle size it is, right. So this is, let's say this name is Peclet number, Peclet number, then L C by D is the Peclet number, which is actually tells the ratio of advective transport rate to diffusive transport rate in a fluid which is under a constant, which is under force. Now Smoluchowski equation actually gave good insights for sedimentation under gravity and this kind of this thing. Now let's a random walk with a sojourn probability, sojourn probability at each site. Let's say we modify the biased random walk in following manner. First, the random walker jumps a step to the right or left with respective probability respective probabilities alpha and beta, or else stays at the same site. So here we are also adding one thing, that it stays at the same site with a probability gamma, which is 1 minus alpha minus beta. Now we have already considered now you can see in continuous random walk thing we have already considered it. So random walk in a continuous time, you can do this, but here there will be some changes. So there, if you see here, there will be a probability gamma which will be at this that relations again. So only thing that will change, we have to add a term gamma p ja n tau minus t in right hand side of equation 17. Now if you do that, then that will only add to this. So when you will reshuffle this, that will add only this term, right? If you add this term, so that will become 1 minus alpha. The diffusion coefficient will become 1 minus alpha, right? This will become only 1 minus alpha, because everything was in that way only. So only thing that will change is that the diffusion constant will change by factor 1 minus alpha, and that will be a reduction. So that will be a reduction to this thing. Okay, so let's continue our discussions for a more generalized thing. So we'll now sort of focus in stochastic processes. Okay, so now we'll go to stochastic processes. So we'll now get into the Mendel. So let's start. Stochastic processes. So far, random walk and all these things, and Brownian motions, positions, whatever you have, we have seen. There, one thing we can say that the positions is not deterministic, right? Like, you cannot predict what it will be in the next step. There will be some probability associated with it, but you cannot say 100% that it will happen. So it is not a deterministic process, it is rather a stochastic process. Okay. So the stochastic process is also named as random processes. Same name. So this is also used in computer science and electrical engineering and all these things. Okay. Okay, first I will say, let's say you have a random variable x. Okay. And it has a sample space which consists of discrete set of n values. Okay. Discrete uh, set of n values of this, let's say x1, x2, discrete set of these values. Okay. Now what you are trying to do is, you let's say, you are writing it as like 1 by 2, you are setting it as like, let's say, state by state, 1 2 3 j. Let's say there is n states, like n points, n values of these random variables. Okay. So whatever, we can also use j1, j2, j3, whatever. So now let's say that the sequences of time is, let sequences of time t1 greater than t2 greater than t3 dot dot dot. So this is an arbitrary sequence of time. Arbitrary. These are also random. Arbitrary sequence of times. So now statistical uh, properties of these random processes are defined by this infinite set of multiple time joint probabilities. So now statistical properties properties statistical properties of the random processes are specified by an infinite infinite set of infinite set of multiple time joint probabilities. Okay, so how that will be? That will be like how it is given this is happening, what is the probability of happening of that in later time. So let's say the first point is P1 J1 T1 P2 J2 T2, sorry, this is JT, this is KT2 given that JT1 or P3, let's say LT3 given that happening KT2 given that happening JT1. Okay, so like these are the now n time joint probability is that how starting from J1 to 1, then there will be J2 T2, there will be J3 T3 like this. So for this is a fresh equation, let's say 1. So for so this is like n time conditional probability. So n time joint probability, then it will be Pn, let's say Jn Tn Jn minus 1 Tn minus 1. So this is J1 T1. That means here what is the probability starting from this, then going J2 T2, then going J3 T3 like this. Okay. So now we can make this as product of conditional probabilities. So we can write this joint probability as sort of uh, product of some conditional probabilities. How? Let's see. Let's see how can we write it. So basically you will write this conditional probability as Pn Pn that reaching Jn giving you are coming to be Jn minus 1 Tn minus 1. These are like the conditional probabilities J1 T1 plus Pn minus 1 Jn minus 1 Tn minus 1 J1 T1, right? Just one step backward, huh? So this is the conditional probability that happening happening this. What is the probability happening this? What is the probability of happening that? It is actually the probability that occurring the state Jn at time Tn, given that events to this right, events to the right of the vertical bar, like this bar, or there is no bar. After this, these events are occurred successively earlier in stated time. Okay, so in turn of, so, so if this is happened, that they sort of happened at successive times and earlier successive times, then we can write this like this. So in that way you can sort of make it. So this joint probability, this means this, so then this mean will be like this times this one, and there will be a bar after Jn minus 1 Tn minus 1. Okay, so from here we can easily write that a stochastic process, a stochastic process is specified is specified by an infinite infinite hierarchy of multiple time conditional probabilities, and only a single probability, that is J1 to 1, only a single time probability P1 of JT. Now this is actually sort of convenient because in all physical problems or applications, probability and random processes, we can only write equations for conditional probabilities. So we will write always the conditional probabilities. So now let's see the two-time conditional probability. That is a next step. So Markov process is like Markov the Markov processes Markov processes can have discrete discrete or continuous sample spaces. Sample spaces. Now, discrete Markov processes may also be different in discrete time, right? And discrete Markov processes, discrete Markov processes may also be defined in Markov times or like discrete time. When they are in discrete time Markov processes, this is called Markov chains. Okay, so there is like various discussions in literature, but here we will discuss in continuous time. Okay, now here it is like Markov processes Markov process uh, Markov process is one with a memory, a certain memory with a memory that is restricted at any instant of time at any instant of time to the immediate preceding time argument. Okay, that means just previous step it can only memory to that step. Okay, immediate to the preceding immediately preceding time argument. So for that we can write easily so this probability of finding state Jn at time Tn is Jn minus 1 Tn minus 1 J1 T1 T2 is equal to J2 T2, sorry, P2 is J1 Jn Tn by Jn minus 1 T minus 1, and for all n greater than 2. So it's we can write in like this. So if it reaches to the point j at time tn, that means if only interested probability from this conditional probability is what is the condition that uh, what will be the probability that if it start from jn at tn, jn minus 1 and tn minus 1, what is the probability of being at jn at after time tn, okay, for all in. Now this single time step memory characterizes a Markov process is equivalent to saying that that future state of the process is only dependent on its present state. So now all these joint probabilities of a Markov process are can be expressed as products of two independent variables, just two independent probabilities rather, and a single time probability pi jt. Okay. So basically we are saying that it does not sort of depend on the earlier steps, only depend on the immediate past uh, steps. Okay, so what he is saying is so products of like this space. So basically the nth step only will be dependent on the n minus 1 step. So the earlier just one step back it will remember the memory, otherwise it will not remember it. Okay, so it is similar to like saying single time step, single time step memory characterizing characterizing a Markov process is equivalent to saying that the state future state of the process is only dependent dependent on its present only depends on its So basically here, so it is dependent on its present state. So if you just think like this, the present state, okay, and not on the history of how the process reached to the present state, huh? and and not on the history of how the process reached the present state. So it's mainly depending upon that. Okay. Okay. So it might sound that it's very, you know, technical assumptions, but it actually leads to a great deal of simplifications, and our calculations will be much more, simpler. So now all our the joint probabilities of a Markov processes, then we can express as products of two independent probabilities, huh? Like a single time probabilities and just two time conditional probabilities, just before that. Okay. So now what we can write then, if it is that process, then I can write Pn. So just a minute, let me. So all the joint probabilities of a Markov process are expressible as products of of just two independent independent probabilities that is, one, the single time probability, which is single time probabilities single time probability which is P1 JT, and second one is the two time conditional probability P2 JT prime, where T prime is less than T. Now if you just apply this process repeatedly to the this equation, let me make it a number. So this is 2, this is 3. So then your Pn, Jn, Tn, Jn minus 1, Tn minus 1, J1, T1, that would become is equal to P2, P2, because there is only the two transitions you want to know, P2, Jn, Tn, Jn minus 1, Tn minus 1 times P2, Jn minus 1, Tn minus 1, Jn minus 2, Tn minus 2 times, if you take the last thing, will be P2, J2, T2, J1, T1 times P1, J1, T1. So this is the single probability, right? So if so this is the now for a stationary random process we can also simplify it further. So if we take a stationary random process is one whose statistical properties do not depend on the choice of on the choice of the origin of time. Origin of time. So like it will be like time, where time starts it does not depend. So that means it's a time translational invariance. So this is similar to time translational invariance. In deterministic dynamics. And sometimes a stationary random process in some mathematical languages or mathematical in literature, they call it a homogeneous random process, because stationarity is the same thing as like homogeneity, because there is no preferred point. So for a stationary random process, for a stationary random process, P1, Jt is independent of time, is independent of time. So we can write P1 Jt is equal to P1 J. Let's say this is 6. Sorry, this is 5. Okay. And the two-time conditional probability then becomes, and P2 K T J T prime, that becomes P2 K T minus T prime, this time difference, and J 0. This is 6. So it only is a function of difference of this to to these things, right? Now you can write this notation as also new definition as P2 K T minus T prime by J. You can also write it like this. So now what we will do is, like, if we change this thing, so then Pn Jn Tn Jn minus 1 Tn minus 1 J1 T1, that actually becomes product of r equal to 1 to n minus 1, because there will be n minus 1 number of pairs, and P Jr plus 1 Tr plus 1 Jr plus 1 Tr plus 1 minus, this will be Tr, this will be Tr, their differences, given that it starts from Jr. Okay, so this is equation 7. This is for every n greater than 2 or greater or equal to 2. At least you have to have one pair. Now in our these discussions, we will always consider stationary processes unless we specify these things. Now let me put here, we will take stationary processes unless otherwise specified. Otherwise specified. Okay. Okay, so now we need inputs for the stationary probabilities, Pj and the conditional probabilities, right? So these are a priori independent quantities, so it does not depend, the stationary probability Pj and the conditional probability, they do not depend on each other, on each other. Okay, so now different calculations or situations modeled by Markov processes, so they are actually sufficient degree of mixing they enjoy. So this is a technical term in dynamical systems. So sometimes, most of the times, the the dynamics underlying underlying the random process random process generally enjoys a sufficient degree of mixing so this mixing property, the what is this mixing property? This mixing property is actually this mixing property ensures that this relation limit t tends to infinity p of k t j is p of k. For mixing property, equation 8 should hold. Okay, so should hold. Now, what does this mean? Now, this means the memory of the initial state j is lost, means as t tends to infinity. Since t is very big, so the initial memory of the initial state is lost, and the conditional probability simply tends to stationary probability pk corresponds to the final state. So the conditional probability simply tends to the stationary probability pk corresponding to the final state corresponding to the final state. Okay, so that will be this thing. Okay, so I will stop here. We will continue our discussions in the next classes, and we will discuss there the Chapman-Kolmogorov equations, and we'll see how different things unfold.